Welcome everyone. Subject name KYM. Fifth unit. Friction in brakes. A brake is a device by means of which artificial frictional resistance is applied to a moving machine member in order to retard or stop the motion of the machine. The capacity of the brake depends upon the following factors. That is the unit of pressure between the braking surfaces, coefficient of friction between the braking surfaces, the peripheral velocity of the braking drum, the projected area of the friction surfaces, and the ability of the brakes to dissipate heat equivalent to the energy being absorbed. And the next one is what are the materials for brake lining. See some of the following characteristics of some of the materials used for brake lining. It should have the high coefficient of friction with a minimum fading, have low wear rate, high heat resistance. The material which having the high heat dissipation capacity, it should have the adequate mechanical strength. It should not be affected by the moisture and oil. The table column shows the properties of the material for brake lining. Material for braking lining. Some of the materials like cast irons, bronze, steels, wood, fiber, cork, leather, etc., asbestos, and relevant coefficient of friction mu, and relevant allowable pressures for different materials, different brake lining materials. And the types of brakes. Different types of brakes are available: hydraulic brakes, electrical brakes, and mechanical brakes. In hydraulic and electrical brakes cannot bring the member to rest and are mostly used where large amount of energy are to be transmitted for the brake is retarding the load, such as in laboratory dynamometers, highway trucks, etc., and locomotives, electrical locomotives. In mechanical brakes, according to the direction of the force acting, it may be divided into the following two categories. First one is the radial brakes. In these brakes, the force acting on the brake drum is in the radial direction. The radial brakes may be subdivided into external brakes and the internal brakes. And the second one is the axial brakes. In these brakes, the force acting on the brake drum is in the axial direction. The axial brakes may be a disc brakes or in cone brakes. And the next one is the single block or shoe brake. The following diagram shows the single block brake. It consists of a block or shoe which is pressed against the rim of the revolving brake wheel drum. The block is made up of softer material than the rim of the wheel. This type of brake is commonly used on railway trains and trams cars. The friction between the block and the wheel causes a tangential braking force to act on the wheel, which retards the rotation of the wheel. The block is pressed against the wheel by a force applied to one end of the lever, to which the block is rigidly fixed. The other end of the lever is pivoted at the fixed fulcrum O. The left hand side diagram shows the brake wheel is rotated in clockwise direction, and the right side diagram shows the rotation in the anti-clockwise direction. Both the diagram, O is the fixed fulcrum point and V is the force acted at a distance of L. Where P is the force applied at the end of the lever, Rn is the normal force pressing the brake block on the wheel, smaller is the radius of the wheel, 2 theta is the angle of contact surface of the block, mu is the coefficient of friction, Ft is the tangential braking force. If the angle of contact is less than 60 degree, then it may be assumed that the normal pressure between the block and the wheel is uniform. In such case, Ft is equal to mu into R1 is equation 1, and the braking torque Tb is equal to Ft into R, that is equal to mu into Rn into small r, that is equation number 2. The picture shows the brakes are on, the pad grip the wheel rim from either side. The friction between the pad and the rim converts the cycle's kinetic energy into heat as they reduce its speed. Now go through the examples, exercise sums. A single block brake is shown in the figure. The diameter of the drum is 250 mm and the angle of contact is 90 degree. If the operating pressure of 700 Newton is applied at the end of the lever and the coefficient of friction between the drum and the lining is 0.35, we want to determine the torque that may be transmitted by the block. So given D is 250 mm, first you write the given things: small d, small r, radius of the drum 125 mm, 2 theta is equal to 2 theta 90 degree, that's converted into pi by 2 into the radius. P is equal to 700 Newton, mu 0.35. Since the angle of contact is greater than 60 degree, therefore equivalent coefficient of friction, the angle of is greater than 60 degree, mu dash is equal to 4 mu sin theta divided by 2 theta plus sin 2 theta. Solving these values, we have to find the mu dash is equal to 0.385. Let Rn is the normal force pressing the block to the brake drum, and Ft is the tangential braking force. Ft is equal to mu dash Rn. Taking moment about the fixed fulcrum O, force into distance. Here 700 Newton force into a distance of 250 plus 200 mm plus Ft into 50 is equal to normal force Rn into 200. That gives the Ft is equal to 670 Newton. Here all things are available. We know that the torque transmitted by the block brake Tb is equal to Ft into small r. Ft we already known 670, and small r is the radius of the drum 125. By solving this, Tb torque transmitted is equal to 83.75 Newton meter. And next chapter, band and block brakes. Band brake may be lined with blocks of woods or other material. The picture shows that the friction between the blocks and the drum provide the braking action. N is the number of blocks, each subtending at an angle 2 theta at the center, and the drum rotates in anti-clockwise direction. Is the picture show in the anti-clockwise direction. T1 is the tension in the tight side, T2 is the tension in the slack side, mu is the coefficient of friction between the block and the drum, T1 dash is the tension in the band between the first and the second block. Meanwhile, T2 dash, T3 dash, etc. is the tension in the band between the second and the third block, between the third and the fourth block. We consider one of the block. In our cases we consider the first block. Then this is in equilibrium under the action of the following forces. T1 is the tension in the tight side, T1 dash is the tension in the slack slide, or tension in the band between the first and the second block. Normal reaction of the drum on the block Rn, the force of friction mu into Rn. Resolving the forces radially, we have T1 plus T1 dash is equal T1 plus T1 dash into sin theta is equal to Rn. This is equation number 1. Resolving the force now tangentially. First resolving the force in radial condition, now resolving the force in tangential conditions. T1 plus T1 dash into cos theta is equal to mu into Rn. That is equation number 2. Dividing equation 2 by 1, we have T1 by T1 dash is equal to 1 plus mu tan theta divided by 1 minus mu tan theta. Similarly, it can be provided for each of the blocks. So Tn minus 1 divided by 2 is equal to 1 plus mu tan theta divided by 1 minus mu tan theta. The braking torque on the drum on the effective radius Re, Tb is equal to T1 minus T2 into Re. Note, for the first block, the tension in the tight side is T1 and the slack side is T1 dash. For the second block, the tension in the tight side is T1 dash and the slack side is the T2 dash. Similarly for a number of blocks. Next, move on to the exercise number 19.11. In the band and block brake shown in this figure, the band is lined with 12 blocks. The 12 blocks means n is equal to 12, small n, each of which subtends at an angle of 15 degree at the center of rotation of the drum. The thickness of the block is 75 mm and the diameter of the drum is 850 mm. When the brake is in action, the greatest and the least tension in the brake straps are T1 and T2. It is shown that T1 by T2 is equal to 1 plus mu tan 7.5 degree divided by 1 minus mu tan 7.5 degree, the whole power 12. The 12 is the small n number of blocks, and also mu is the coefficient of friction. Within the lever arrangement as shown in the figure, we have to find the least force required at C for the blocks to absorb 225 kilowatt at 240 rpm, and the coefficient of friction between the band and the block is 0.4. First you have to see the pictures. Circular wheel of diameter 850 mm and it having the blocks of 12 numbers. So the solutions, first you have to write the given details. What are the details given in the questions? Number of blocks 12, 2 theta is equal to 15 degree, theta is equal to 7.5 degree, small t 75 mm and small t 850 mm, power 225 kilowatt, n speed 240 rpm, mu 0.4. You have to consider since 0 OA greater than OB, therefore the force at the C must act downward direction. OA 150 is greater than OB, that is 30. 150 is greater than OB. So the force acting on P is in the downward direction. First you have to assure that. Let's go for the which one is the tight side and slack side. In this condition, T1 is the tight side and T1 dash is the slack side for the first block, and Rn is the normal reaction, the force of the friction mu into Rn. First, resolving the forces in radially, T1 plus T1 dash into sine 7.5 degrees equal to Rn. So equation number 1. Now resolving the forces in tangentially, T1 minus T1 dash into cos 7.5 degree is equal to mu into Rn. It is equation number 2. Dividing equation 2 by 1, we have T1 minus T1 dash divided by T1 plus T1 dash is equal to mu tan 7.5 degree, because cos by sine is equal to tan 7.5 degree. Substituting these values, we have to get the T1 divided by T1 dash is equal to 1 plus mu tan 7.5 degree divided by 1 minus mu tan 7.5 degree. Similarly, for the other blocks, T1 dash divided by T2 dash is equal to T2 dash divided by T3 dash, etc. Remain constant. So for 12 blocks having the greatest tension T1 and the least tension is T2, T1 by T2 is equal to 1 plus mu tan 7.5 degree divided by 1 minus tan 7.5 degree, the whole power 12. Next, we have to find the least force required at C. The force, the least force P is equal to least force required at C. We know that the diameter of the band, capital D, is equal to small t plus 2t. That is small d is equal to 0.85 plus t is 0.075. You have to substitute these values to find the diameter of the band. D is equal to 1 meter. The power absorbed, T1 minus T2 into pi dn divided by 60. Solve by given known things. Unknown value T1 by T2 taken as in the right side. Power into 60 divided by pi dn. So T1 minus T2 is equal to 17,900 Newton. Consider it as the equation number 3. We have to prove that T1 by T2 is equal to 1 plus mu tan 7.5 degree divided by 1 minus mu tan 7.5 degree, the whole power 12. Substitute these values. We already know mu value 0.4 and tan 7.5 degree values. I have to get the T1 by T2 is equal to 3.55. Consider it as the equation number 4. From equation 3 and 4, we have to find the T1 and T2. Equating this third and fourth equations, we have to get the T1 is equal to 24,920 Newton and T2 is equal to 7,020 Newton. Now taking moment about the fulcrum, or the fixed fulcrum O, force into direction, force P into 500 is equal to T2 into 150 minus T1 into 30. By solving this equation, we already know T2 and T1. Substitute these values in these equations to find out the least force required at C. P is equal to 610.8 Newton. The force required at C. That is the least force. And move on to the next exercise problem. A band and a block brake having 14 blocks, each of which subtends at an angle of 15 degree at the center, is applied to a drum of 1 meter effective diameter. The drum and the flywheel mounted on the same shaft as a mass of 2000 kg and combined radius of gyration of 500 mm. The two ends of the bands are attached to pin on opposite sides of the brake lever at a distance of 30 mm and 120 mm from the fulcrum. If the force of 200 Newton is applied at a distance of 750 mm from the fulcrum, we have to find the maximum braking torque and angular retardation of the drum, time taken by the system to come to rest from the rated speed of 360 rpm, and the given coefficient of friction between the block and the drum may be taken as the 0.25. Solution. First given things are written. Number of blocks 14, 2 theta is equal to 15 degree, theta 7.5 degree, and given things. First we have to find the maximum braking torque. The braking torque will be a maximum when OB greater than OA. See the diagram here. OA and OB. So OB is greater than OA. 120 is greater than OA. So the braking torque will be maximum when OB is greater than OA, and then the drum rotates anti-clockwise as shown in the figure. The arrow mark shows the anti-clockwise direction. The force P must act upwards and the end of the band attached to A in tight under the tension T1, and the end of the band attached to B is in the slack under the tension. So T1 is the tight sides and T2 is the slack side at B section. Now taking moment about the fixed fulcrum O, the force into distance at point C, 200 Newton force, 200 into at a distance of 750 at a fixed fulcrum, plus T1 into 30 is equal to T2 into 120. By solving this equation, 12 T2 minus 3 T1 is equal to 15,000. Consider it as the first equation. We know that tension on the tight and slack side, T1 divided by T2 is equal to 1 plus mu tan theta divided by 1 minus mu tan theta the whole power n. We already know the mu value, it is in given, and theta also given. Substitute these values. We have to find the T1 divided by T2 is equal to 2.512. Consider it as the equation number 2. First equation, from equation 1 and 2 we have to find out the T1 and T2. By solving the equation 1 and 2, first equation 12T2 minus 3T1 is equal to 15,000, and the second equation T1 divided by T2 is equal to 2.512. Solving this equation, we have to get the T1 is equal to 8,440 Newton and T2 is equal to 3,360 Newton. We know that maximum braking torque TB is equal to T1 minus T2 into small r. We already know T1 and T2 and small r. So TB is equal to maximum braking torque TB is equal to 2540 Newton per meter. And the second one is to have to find out the angular retardation of the drum. Let alpha is the angular retardation of the drum. We have the known braking torque TB, 2540 is equal to I into alpha is equal to m k square into alpha. Substituting these values, we have to find the angular retardation of the drum. Alpha is equal to 5.08 radiation per second square, and last we have to find out the time taken by the system to come to rest. Let small t is the time required. Since the system is to come to rest from the rated speed of 360 rpm, therefore initial angular speed omega 1 is equal to 2 pi into 360 divided by 60. That gives the omega 1 is equal to 37.7 radians per second. and the final angular velocity come to rest. So omega 2 is equal to 0. We know that omega 2 is equal to omega 1 minus alpha into t. Substituting these values, t is equal to omega 1 divided by alpha, that gives the required time. Small t is equal to 7.42 seconds. Thank you.